Thanks, Dr. Ron. First of all, we very much appreciate the opportunity to come out and share some of our experiences with you. And I would like to congratulate Dr. Rahman for inviting us. When we were preparing for it, I actually was thinking, well, how can we make this effective for this class? And so I start by saying, actually, 23 years ago, I was sitting in this class. So we're trying to structure this so that we can put a little bit of, I'll call it, meat around the bones for what you're learning practically and how it applies actually in industry. So the presentation that we've got is about 20 minutes long. We would ask that you hold your questions till the end, and then we'll have probably a 3 or 4 minute discussion period then. And with that, I guess we'll get going here. So our main topic here, so we call it the practical side of heat transfer, and we're here to talk about heat exchange. So a little background on the company that myself and my colleagues work for. We're from a company called Alberta Industries. It's based here in Edmonton. We've got a fabrication shop on the south side. It's about 20,000 square feet and on 4 acres. We do have about 150 employees, and we do peak up around 300. The division that I'm with now, we're on the maintenance side, so we deal a lot with the plants and shutdowns and servicing of heat exchangers. So we can ramp up to that high. For capabilities, some of the things that will be of interest to this group here, we can design for internal pressures up to 3,000 psi. We do work with all sorts of materials, carbon, steel, low alloy, stainless, nickel, any proprietary materials such as Hastelloy and Inconel. Heat exchangers you see in all sorts of different materials, all sorts of different services, and quite often critical, harsh service. The largest unit that we've ever built is in excess of 450,000 pounds, and we've got in excess of 200 weld receivers. So the main 2 topics we're going to talk about today, I'm going to deal mainly with mechanical, and then Baljeet will go with the thermal. Always a good spot, I was told, to start a presentation was with the definition. So I should probably ask the group here what the definition of heat transfer is, because Webster, what they say is it's the movement of heat from one body to another. So that's a gas, liquid, solid, or any combination thereof. So that's multi-phase flow, and I'm not sure if you've got into that yet in your studies, but definitely we work with that all the time. And for a heat exchanger, the definition of that is it's a piece of equipment to transfer heat. So it's built to efficiently transfer the heat from one medium to another. And in industry, the most common type of heat exchanger that you will see is the shell and tube heat exchanger. And I'll go through what the different parts of a heat exchanger are a little bit later. This slide here, I think, is of value to you. Basically, I tried to capture what industries use this type of equipment and what they would be called. So as you set forth in your careers and even some of your studies, in between terms, where would you see these? You'll see them all over, basically. So petrochemical, so all oil and gas and chemical, pulp and paper, power industries, fertilizer. Anybody working in SAGD, there are hundreds of thousands of these. That's where Mike and I work with, mostly up in Fort McMurray, and there's just literally thousands of these. For what do you call these things? There's a lot of names you'll see. I haven't got them all yet. Condensers, evaporators, boilers, chillers, coolers, reboilers, you name it. There's a lot of names. So those are all heat exchangers. How does it work? I've got a pictorial here right away. But essentially, you've got one product on the tube side, one product on the shell side, and you've got membranes in between that transfer heat. It is mainly the tubes, as you will see, but anywhere where there's a membrane in between the shell side and the tube side, you will get heat transfer. So this is my animation. If you can follow the yellow arrow, that is the tube side fluid. So that is, it comes in on the front end of the tube, or on the channel, and that is a B type, and Baljeet will explain that later. Comes in the inlet nozzle on the bottom. If you follow the yellow arrow, goes down the tubes, goes around the U-bend on the bundle, comes back out, and exits out of the top of the channel on the left side, out of the outlet nozzle on the channel. There's a tube sheet that separates the front channel and the shell, and that's there's 3 plates there you can see. And on the right-hand side is your shell. So that's an E-type shell, which means it's a single-pass shell, and a U-type rear end. So the fluid on the shell side, how it comes in through the top nozzle on the shell. That's the red fluid. It's a cross-flow exchanger. It moves itself around the segmental baffles and exits in the shell nozzle at the bottom. So most of the heat transfer will occur in this exchanger across the tubes. This is what it looks like in real life. We build these things all the time. This is about a 50-inch diameter exchanger. A little bit different style, a little different team of style. This is an AFU, we call it. So the front head, it's called the channel, and I've got in brackets tube side. That's an A-style front head. And then there's a tube sheet in between the two, and I've got it identified on the picture there. And it's got a bundle that is inside that shell with all the tubes in it. And then there's the shell, which is a number of plates that are put together. So breaking it into components now. The very first one is the one I was referring to as the channel. That's the A component in the last slide. This is how it looks in our shop. So this is a piece of plate that's got two flanges on it. It's got two nozzles. And then we will put a divider plate in there, so that way it will have a pass plate, it's called. And the fluid will come in one nozzle, go down the bundle, come back out, and exit. This is the bundle. So the bundle is the heart and soul of the heat exchanger. You can see there's lots and lots of tubes. It takes a tremendous amount of man-hours to make these things. The top left picture shows it from the front. That's the tube sheet with all the tubes that are stabbed into the tube sheet. How we attach those is we weld the ends of them. In this particular case, we don't always weld, but we also roller expand, it's called. So you've got ring grooves in your tube sheet, and then you roller expand the tubes into it, and that secures it. That's how you hold your tube in there. The bottom right picture is the U-bend, and in this particular type of bundle, that's how the tube side fluid gets back to the front. This is a shell. There's no magic to this. This is a pressure vessel. So anybody that's worked with pressure vessels before, this is a typical pressure vessel. You've got a number of cylindrical shells that are all welded together, and then you'll either put a head or a flange on each end, and then you stab your bundle in it with your channel on. That's how you manufacture. How to design, I've already said we've got two things that we consider, thermal and mechanical. But some of the main design considerations that you really need to take into account as you begin a design are fabrication. You have to answer these questions. Can it be built? Okay, you can design the best heat exchanger in the world, the most efficient, but if you cannot build it, it's the worst heat exchanger. So you really have to take into account a lot of factors. You work with your operations people, and Paul G's got some other things he'll talk about too. Cost effective. It's got to be cost effective, otherwise there's no sense. Your client's not going to buy it. And then maintenance, and this is what Mike and I deal with. Can you maintain this heat exchanger? Heat exchangers typically have fluids in them that will foul. And if you're familiar with the term fouling, what that means is there will be an accumulation of deposits in the heat exchanger. So you need to be able to disassemble them, clean them, and put them back together. So that's some of the questions that you need to answer and you work with your clients on. Mechanical design considerations. There's three that I've identified here. Engineering fundamentals, legislated codes and standards, and specifications. Breaking them into each of the three. Engineering fundamentals are what you're learning here at university. It is also your experiences that you're having in your work terms and any of the experiences you have after you graduate. Your interaction with your colleagues and your mentors, all those things form the basis of your engineering fundamentals. I like this slide here because, as I said, when I was sitting here 23 years ago, I wasn't really sure how all these courses that I was taking were going to apply, to my work life later. Now I do kind of get it. So I've got a number of the mechanical engineering courses identified here that we use every day. So I'll go through them, and I won't talk about them individually. You know them. So MECI 364, that's basically how you build things. So that manufacturing process is very applicable. MECI 380 gets into your membrane theory, how you design a pressure vessel. There's some advanced strength materials as well for designing your saddles, your lift lugs, all those type of things that inputs into this design. And then the process design side of it, which we'll talk about in great detail here shortly, that's the heart and soul. So that's the big, I don't know what the, I've got there, big 230, 340, 370, and 330. All your mechanical engineering courses, use those every day. Absolutely, every day that we design, that's the ones we use. Some other things that are very important that you've learned, your 250 course, your 265, and your 300. I use those all the time. So, for legislated codes and standards, by legislated it means it's law. You have to follow them. So So these are the codes that we use to design mechanically these heat exchangers. The ASME is the American Society of Mechanical Engineers. They've got a set of standards called the Boiler and Pressure Vessel Code, sections 1, 4, 8. There's a number of documents there. And that is I'll call it a soup to nuts design code. It's all about breakthrough materials, design, to testing, and then tolerances, all of that. So Canadian code is the CSA B51, that's for boilers and pressure vessels, and then there's another one called the TEMA code, which is a tubular exchanger manufacturer's code. All those are legislated codes that we have to follow. For specifications, it's not legislated. The American Petroleum Institute has specification 660 for shell and tube heat exchangers, and then we use client specifications and our own internal fabricator specifications. So those aren't law, but we do have to follow. I'm going to turn it over to my colleague now, Paul G.
Good afternoon, everybody. Hopefully everybody can hear me. My voice is as not loud as Dave's. So we're going to talk about thermal design of heat exchangers. As you know, we're studying heat exchangers. There are so many types, right? Shell and tube heat exchangers, spiral heat exchangers, plate and flame exchangers, air coolers, economizers. As they said, you can name it. But as a company, Atex, we specialize in shell and tube heat exchangers. To design those, we don't do any hand cuts. Thank you. But we use some softwares, HCI and Aspen. So these are the pretty industry recognized softwares to design the shell and tube heat exchangers. So designing a shell and tube heat exchanger, we will get an inquiry from our client to design an exchanger to perform certain duty. As Dr. Raman mentioned that you guys love equations, so I put one in there. Q is equal to M times Cp times delta T. This Q is your flow rate, Q is your duty, M is your flow rate, Cp is your specific heat, and T1, T2 is inlet outlet temperatures. Important thing to note once you receive this information always comes from client. They provide you the process information for shell side and for tube side. So shell side duty have to balance with tube side duty. So shell side duty is equal to the tube side duty, which is the duty of the exchange or heat exchange by an exchange. So what is the minimum data required to size an exchanger? First of all, you need shell side and tube side properties. Without any properties, you can't size exchanger. For single phase fluids, it's much easier to size exchanger because you need just properties at inlet pressure and at inlet and outlet temperatures. The properties require are density, viscosity, specific heat, and thermal conductivity. Once you have those, you're good. And once you have the shell side and tube side properties, the next thing is to come up with certain geometry, called TEMA type. What is going to be your front head? What type of shell you need? What type of rear head you need? So I think I handed out some TEMA charts as well. We were short, so I can do this one speaking of those. So if you look, the first column, these are the front heads. It shows A type, B type, C type, N type, D type. Every head has its own importance. Like A type can be used where you want a quick inspection of the tube and you want to remove the bundle. And you can replace that with cheaper B type head because you're not putting additional flange and cover on there. You just do welding a semi-elliptical head. So depending on if you have high pressure exchanger, then you would want to use the D type head. The same thing on the second column, which shows the different type of shells you can have, like E type and F type. So E type is one pass shell, where F type is two pass shell. So if there is a temperature cross in E shell, you have to have two shells in series to eliminate that temperature cross. To make it cheaper, you can make as an F shell. So you separated that shell into two shells. Then K type, it's a camel boiler, as explains there is a lot of ventilation going on, so you need K type shell. Same thing on the rear heads. So how do you exchanger. Normally, when we talk in industry, somebody will tell us 23 to 40 BEU. What does that mean? So 23 is the 23-inch shell ID, and 240 is the tube statement, and BEU is the TEMA type you selected. B is your front head, E is your shell, and U is your rear head. So that's the way you form a TEMA type. So other things to consider once you have this information, you have to apply, as Dave mentioned, through customer specifications, all the ASME codes and that stuff. A lot of inquiries you get when the EPC companies, the new engineers, when you guys go out, come up with a very cheap exchanger, but with a quite a bit long length of the tubes, which is not available in the market, or if it is available, it's available on special orders. Right? So that's not reducing the cost, actually, that's increasing the cost. And it will be really hard to maintain as well, because if your tubes are plugged, you can't get the tubes in real quick. Tubing delivery is 22 to 24 weeks. So either you buy another exchanger, keep it spare. It can be done on special high pressure designs. Because in high pressure designs are the only design you want to make them exchanges longer, not bigger in the diameter. Because if you grow in the diameter, every thickness due to the code, like flanges, your tube sheet, the stud diameter start going up. So you make it longer to keep it small diameter. As I said, you can get tubes more than 75 feet long as well. Practical problem. Last year, 2010, we had one of our clients came with a problem. They had some plugging issues with one of their exchangers. Just keep plugging every 3 or 4 months. So they had to do chemical cleaning and stop the work, right? It's a downtime, it's money. So existing exchanger was 160 BEU with 3/4 inch 18-gauge stainless steel tubes. And falling factor 000352. Okay. Whenever we size exchanger, we always size for fully forward ignition. So this falling factor needs to come from our customer. They specify falling factor for certain tubes, and we always size exchanger in fully forward ignition. But when they fall more than they're supposed to, then they plug. So there is no heat exchange. And the velocity on the tube side was below 1 meter per second. We're talking condensate cooler here, water exchanger on both sides. You guys have the TEMA sheet. This is the improved design we had. So the solution we came up with, we put 1-inch tubes versus 3/4 inch tubes, and we taken out the U bends because most of the time it plugged on the U bends. We put the 1-inch tubes so you can mechanically clean it if you need to, and we put the more classes, like I think this one is 6 pass, and velocity we made it on tube side 1.47 meters per second. And good thing it's in service from here to 12 months. So no phone call. It's always good. So no plugging issue. So this is the TEMA sheet. I wanted to show you the actual HDRI program we had, but some reason we cannot connect my laptop to the projector, so we had to miss out on that. So, any questions? Any questions?
I know we have lots of questions, so please ask. Do you guys, for fouling, like, is there certain materials that, like, are more conducive to fouling? In terms of, like, do you guys pick certain materials to reduce fouling?
We don't check the materials.
No,
Material is specified by customer. Because it depends on the process condition, if they are exchanging corrosive service or roads. So they specify. Good thing in thermal design, we just have to specify the tubing material. That's carbon steel, stainless, duplex. Fouling is when you run through liquid over a surface, it's a tendency to deposit. So deposit is called fouling.
An extreme example of fouling, Mike and I deal with quite often up at Sag
keep, if we're talking falling on the shell side, when you're designing, you want to design that with 90-degree pitch, so you can mechanically go into it. If you're designing on the tube side, you want to keep as we did in this case, we put 1 inch tube. 352 is the borderline for the tubing, and for the shell side, in this case, I think pitch is 30 degree. I don't know if I can point on the data sheet. If you guys look here, the layout is 30 degree. So, because the falling on the shell side is 0001. So if that was 000352 on the shell side as well, first of all, we cannot use any type exchanges because you can't open it up. It's a welded tube sheet on both sides. So you have to go with the removable bundle on that side. And you have to go square pitch so you can take the bundle out and you can do it again.
As the video shows the slide.
The animations that they showed.
What kind of configuration?
Configuration for the tubes. For the tubes?
Oh, like the pitch?
I think isn't that because we still not over. So we have just covered that bundle of tubes. That's a different problem. That's not detected type of problem. So he was asking that whether it is standard mode or allied mode, but that is different. That's not seriously different. What were the softwares you said you used for design?
Sorry.
What were the softwares?
Software,
Yeah.
HDI and AspinTech. AspinTech has a lot of products in that particular one is Task Plus.
Yeah, Aspen also has the HYSYS. Maybe we've heard of HYSYS before. So if this is a little further down to the design, like I think design would be cheaper on the HYSYS. Yeah, that's the process now.
Any question from this side? I'm only asking from this side.
They're winning because we.
Yeah, maybe I'm standing on this side.
Yeah. On the shell side, I know that there's a number of sticker.
Yeah, those are called baffles. So how do you go about that? There is a TMA requirement. You have to have within 48 inch the maximum space you can go. You can go up to 60 inch, but the maximum recommended is 48. Because after that you have to start having some vibration issues. You can go a little smaller than that. But those are the baffles that help you increase or decrease your flow velocity to get the maximum heat transfer.
There's also different types of bathroom arrangements. Like the one that we showed is a single segmental. You can have double segmental, you can have triple as well. So there's a whole variety of them. It's just all how it flows. It looks like a perforated plate. So what we do is in the shop, we take a circle and then we cut it and we drill holes in it and we extract tubes through it.
I think you said a typical flow velocity was 1 meter a second.
It's for the water.
Okay.
For different fluids, it can be different. Like for water industries, that was close to 1.5 meter per second.
Why would
And
you
it
want
always,
faster?
sorry,
Sorry, why wouldn't you want to go faster than that?
if you can go up to 2.6 or 2.9 meter per second. It depending on material. Like this one is stainless steel, you can go in there over 2 meter per second, but you want to hit minimum 1.5 to reduce the falling. But you don't want to go too much higher because that will start erosion issues.
Any other question? Any question?
For bitumen, if you're trying to pump bitumen with that, you pump it at significantly higher velocities, such as a water would, because it's very, very.
Yeah, no, not necessarily, but you want to heat it up. Yeah.
So you heat it up and then you
Yeah.
make it flow.
Yeah.
Just-
I can do all of it, but you might be- Off my head.
Second price.
I do have a question.
most critical in design, in design engineering. And again, 5 or 3 parameters that you need to take into considerations from the safety point of view. So which are those points? Like cost, you mentioned cost is one of the things. What are the other things?
Cost is the least, from the safety point of view.
Yeah. In terms of safety, you know, it's inherent in the legislative codes that we have. It's such a highly regulated industry that I would think that, you know, most of the checks and balances are already in place by regulations. So we have to follow very specific code designs, very specific welding and fabrication methodologies. And then we've got inspectors that are in our shop every day. So we've got government inspectors inspecting because, you know, if you ever hear stories years and years ago about boilers blowing up, that, you know, that just led to all these codes and standards. So from the safety perspective, I think from the, you know, the mechanical side at least, on the thermal side, I can't really think much on the safety. Now your other question was on.
Design considerations. So costing would be one of the.
Then that is, yeah. Whether or not, I mean, I posed it in part of what I was presenting. Can it be fabricated? So Baljeet alluded to it, the footprint. I mean, we have to be very cognizant of how big this exchange is going to be. You won't find as a rule, I mean, in the package of, and I forgot to talk about it, in the package that we passed out there, I mean, the biggest heat exchange that we've ever worked on is about 13-foot diameter. So it doesn't get much bigger than that. So you've got to stay within a certain footprint. And yeah, because it's such high pressure.
We did that on site too.
Yeah. Yeah, that one on the side. So I'm not sure if that really answers the question. Yeah.
So,
Your pressure vessel, do you fabricate that or is that prefabricated?
No, we fabricate. Yeah. So it's very, it's a very distinct pattern that it follows. We deal with the client first, so they give us the process parameters, and we size it, and we interact back and forth with them. And then once we size it, then we mechanically design. They all kind of go hand in hand, but it's first thermal size and you know, process design first, and then mechanical design. Yeah, and then we build it. We build it.
What's the average labor time to build one of the exchanges?
Oh, it's quite a while.
It depends the shop availability, but if you say there is nothing holding up and all material is 6 to 8 weeks delivery, you're looking at one NN we talk. It's a pretty small exchange. You can do that in 12 to 14 weeks. But if we're talking about, again, cost is the consideration, right? We're bringing tubes from China tubing within this 24 to 26 weeks. So after that, we need another 4 to 6 weeks to complete that.
So it's better to maybe make it bigger than expected. Just so people like it was required to get what 3/4 of the tube from each diameter. So it's easier to do.
That's it. See if you had the issues plugging on the U-bend. You probably had usually 1-inch tube with the U-bend as well. The only reasons we didn't go with the U-bend, and again, actually put fabric on both covers. So in half an hour on both sides, you can open the covers, inspect the tubes, and if you have to do mechanical cleaning, you can push the lower fins, do mechanical cleaning,